Thank you for joining this presentation. My name is Bamgboye, and over the next few minutes, I look forward to sharing the results of my master's level research project. In this work, we looked at modelling radial cracks in silicon carbide fibre-reinforced silicon carbide matrix composite cladding using peridynamics. In particular, we wanted to see the effect of incorporating anisotropy onto the crack patterns which formed in the r-theta plane of a SiC-based cladding. Fuel cladding encases the fuel pins and is needed to provide a gas-tight seal against the release of radionuclides. In addition, it must be suitably thermal conductive to conduct heat from the fuel over to the coolant to generate electricity. As such, cladding requires radiation resistance, good thermal properties, high temperature strength, and high temperature oxidation resistance, particularly against high temperature steam. So why is silicon carbide composites being considered as a potential replacement material for the zirconium-based alloys which are currently used in commercial light water reactor claddings today? Well, as we can see from the 2011 Fukushima Daiichi accident, under certain conditions, such as a loss of coolant accident, the oxidation of zirconium occurs. This is itself an exothermic reaction, making the whole thing autogasolytic and reducing the time available to respond to the accident. On the right-hand side, we can see a graph showing the various oxidation rates for different materials. We can see that silicon carbide has an oxidation resistance which is 2 orders of magnitude lower than that of zirconium. As a result, by using silicon carbide, we can increase the grace time, the time available to respond to accident conditions, and then we can also leverage silicon carbide's other favourable properties for a potential nuclear application. Focusing more on the silicon carbide material system, we can see that nuclear grade SiC-SiC varies to aerospace SiC-SiC. In particular, nuclear grade SiC-SiC uses generation 3 silicon carbide fibres. These are high purity near stoichiometric fibres which are wound around a mandrel before a carbon interface material is deposited. Next, a matrix is deposited normally via one of 2 fabrication methods, and the results shown in this work have been done using materials data gathered from CVI SiC-SiC. There are several barriers to the commercial deployment of SiC-SiC in existing reactors. Number 1 is SiC-SiC susceptibility to hydrothermal corrosion. Number 2 are the manufacturing challenges regarding the scaling the manufacture of the production of silicon carbide composites, and secondly, the challenges with regards to producing a hermetically sealed joint between the silicon carbide tubing and the end cap that goes on the end. And the final challenge, which is the focus of this work, is the propensity of silicon carbide composites to microcrack under the loading conditions found in typical light water reactors under normal operating conditions. This microcracking occurs due to the pseudoductile nature of SiC-SiC composites. We can see that at the PLS, we see the onset of matrix cracking, and in the graceful failure period, we see that cracks are deflected by the fibre matrix interface, and that we see also fibre pullout, as well as fibre breakage at the strain to failure. Given the propensity for SiC-SiC tubing to undergo microcracking during the operating conditions found during normal reactor loading, it becomes important to accurately be able to predict the crack patterns that would form in a SiC-SiC clad. Thus, this work aimed to augment an existing peridynamic model created by Haynes et al. To account for the elastic anisotropy which is found in the composite. The crack patterns are then compared between the anisotropic model and the isotropic model to determine the impact of actually incorporating this anisotropy. Peridynamics is a continuum mechanics technique which exists in 2 forms. In this work, bond-based peridynamics is used. In bond-based peridynamics, a material is represented by material points, and each material point experiences a pairwise force from other material points which lie within a horizon of the central material point. These bonds, when stretched over a critical length, are then said to be broken and no longer sustain load, so load is transferred to the surrounding points. Unlike finite element analysis, peridynamics formulates Newton's laws of motion using integrals rather than differentials. This gives rise to its beneficial properties. In particular, peridynamics doesn't require any special treatment in order to deal with discontinuities such as cracks or interfaces. It's able to model cracks without prior knowledge of their deformation mode or their crack pathway. And it also works well for modeling crack coalescence and branching. Some of the disadvantages of using peridynamics include the fact that edge effects occur at the surface, where there are fewer bonds than in the bulk, so there are less bonds than there would be in a normal horizon. Additionally, with bond-based peridynamics, there are limits to the Poisson's ratio, and the Poisson's ratio is fixed to 0.25 for plane strain and 0.33 for plane stress. Additionally, a disadvantage is the computational intensiveness of peridynamics. In this particular work, peridynamics was implemented in Abacus. In this implementation, the Abacus trusses represent the peridynamic bonds, whereas the Abacus nodes represent the material points. In the isotropic case, the elastic modulus of the elastic trusses was constant, but in the anisotropic case, the elastic modulus was set to have an angular dependency. In this work, we modelled 3 types of SiC-SiC cladding architecture, 1 fully composite model and 2 duplex models. In the duplex models, a monolithic layer of CVD is represented, and this monolithic layer is there to provide a hermetic seal, given that the porosity of SiC-SiC composites by themselves means that they don't provide a gas-type seal against the release of radionuclides. So there are 4 main contributors to clad loading in light water reactors. The main 2 are the thermal gradient and the swelling gradient, which occur across the clad. Additionally, there's fission gas pressure, as well as a coolant pressure from the surrounding pressurized liquid. This results in a tensile inner region of the clad and a compressive outer region of the clad. This work modelled the typical conditions found in a PWR reactor, including 2 18-month fuel cycles, plus a reactor shutdown to simulate a refueling outage. As we can see from the diagram on the right, during normal operation, the thermal gradient actually decreases the magnitude of the tensile and compressive stress fields found in the clad. However, upon reactor shutdown, the magnitude of the compressive and tensile stress fields found in the outer and inner surfaces of the clad respectively increases. This leads to cracking and damage being found during the onset of reactor shutdown. In all the simulations shown following the slide, the images are taken from the end of the simulation, so once both 18-month cycles have been completed. In the fully composite architecture of cladding, in both the anisotropic and isotropic model, no damage was found, and hence the results are not reported in this presentation. Looking now at the outer monolith duplex model, we see that fracture is predicted in the outer monolith of both the isotropic and anisotropic model, with minor levels of broken bonds on the outer surface of the monolith. We see slightly more broken bonds in the anisotropic model, and we see fiber pullouts inside the composite regions of both models. It's likely that the cause of these minor damages on the outer surface of the cladding material simulation occurs because during the onset of reactor shutdown, we see a large increase in the compressive hoop stress, so the hoop stress coming along this direction, which would result in a tensile radial stress, leading to some minor bond breaking. However, because the hoop stress is the dominant stress and it is compressive, the ability for this damage to propagate is curtailed, given that the tensile stress field would be at least an order of magnitude lower than that of the compressive hoop stress field. In the inner monolith duplex model, we actually see substantial differences in the appearance of the cracks that are formed in the isotropic and anisotropic models. In the anisotropic model, we can see crack branching. This is likely to stem from greater magnitude of stress reflection waves due to the difference in elastic properties between the inner monolith and the anisotropic composite in comparison to the isotropic composite and the inner monolith. When we look at the effect of reactor power on the damage predicted, we see that the anisotropic model predicts higher levels of damage than the isotropic model. We can also see that the relative fuel power increases the amount of damage seen in both models. More noticeably, when we look at the anisotropic model, we see that at a lower power, delamination of the composite monolith interface is predicted than in the isotropic model. When we look at the effect of the initial thermal conductivity input into the model and the effect of the damage predicted by the model, we find that the anisotropic model is highly sensitive to the amount of damage to the thermal conductivity initially set. We see that with higher levels of thermal conductivity, we see much lower levels of damage compared to when we have low levels of thermal conductivity. To conclude, the anisotropic model consistently reports greater amounts of damage than the isotropic model. The damage level predicted is also sensitive to the reactor power and thermal conductivity. We see that in terms of implications for gas hermeticity, the outer monolith model looks like it could be a suitable candidate, given that damage does not propagate through the monolith despite initiating on the outer surface of the clad. We also see that the inner monolith does show that the cracks will propagate throughout the monolith, and that the anisotropic model specifically predicts delamination at lower powers than is predicted by the isotropic model.